Oh,
Pretty chilling.
cool. Okay, so for the next couple lectures, we're just going to kind of tie up some loose ends with radiation and introduce a few more concepts that kind of just fill in some of the concepts that we learned last week. So taking it a little further than just talking about black body radiation exchange, for example. So we talked about last week, we finished up by deriving the view factor and then writing down some expressions for how to calculate the radiation exchange between two surfaces using the view factor. So that was this equation. And this was for two black body surfaces. And then we said for an enclosure of black body surfaces, we can basically just sum up over all of the receiving surfaces to get the net radiation transfer from a surface of interest, surface I. So that's where we ended last week. And then for today and Wednesday, I want to talk about relating the radiation expressions that we've kind of derived over the past few incidences of talking about radiation. So this isn't material that you'll be tested on or have homework on, but hopefully it will just deepen your understanding a little bit. So the expressions that we have now are radiation exchange between two black body surfaces, and then an enclosure of black body surfaces. Okay, so those are the expressions that we had last week. And then we've also used the equation for the net radiation exchange between a small surface and much larger isothermal surroundings. And that's the equation that we introduced when we first talked about radiation and that we used for the lab. And there are some assumptions inherent in this equation that we just kind of went with. But we're actually going to get into the details of what those assumptions are and when they're applicable. So that was sigma, or epsilon, sigma A, so emissivity, Stefan-Boltzmann constant, times the area of the surface. The temperature of the surface raised to the fourth minus the temperature of the surroundings raised to the fourth. So we're going to talk about how these expressions are related. And what assumptions go into developing this expression down here. So we need to introduce several more concepts before we can kind of circle back to this. So the first concept we're going to talk about is radiation inside a cavity or an enclosure. And last week when we were going through blackbody radiation, the blackbody radiation section, we just briefly mentioned that no surface is perfectly a blackbody, but radiation inside a cavity or an enclosure that's at a uniform temperature is the closest approximation to a real surface that acts like a blackbody. So we'll talk about why that's true specifically. So a cavity whose inner surface is at a uniform temperature is the closest approximation of a black body. So you may already be able to see where we're going with this. We basically treat the surroundings, because they are much larger and isothermal, we're able to treat the surroundings for this equation like a blackbody cavity. So that's kind of where we're headed and why we're talking about this. So imagine just an empty enclosure, and then if you have radiation entering the enclosure through a very small opening, it would basically experience a bunch of reflections within the cavity before reemerging, if it even did reemerge. And that would result in all of the radiation entering the cavity being absorbed, which is the property of a black body. So regardless of the properties of the surface, even if the surface is highly reflecting, that just means that the radiation entering the cavity is going to experience more reflections, but each time it's reflected off the surface of the cavity, some of it is absorbed. So eventually all of it will be absorbed regardless of the properties of the inner surface of the cavity. So that's why it basically acts like a blackbody surface. So we'll say radiation entering the cavity experiences many reflections. And some radiation is absorbed. Upon each reflection. And then eventually almost all of the radiation is absorbed. approximating black body behavior. So since the radiation field inside the cavity approximates a black body radiation field, any small surfaces in that cavity experience black body irradiation. So as long as the surfaces in the cavity are small, such that they don't significantly affect the radiation field, they experience black body irradiation. So small objects in the cavity experience black body irradiation. And this is true regardless of the properties of the inner surface. So like I said, if it's a reflective material, the radiation just experiences more reflections, but is eventually all absorbed. If it's in a highly absorbing material, experiences fewer reflections, and it's all absorbed more quickly. Okay, so this will allow us to treat kind of any room or large isothermal surroundings as a black body cavity. And you can think eventually any of the radiation emitted from an object in that room will be reflected and then eventually absorbed. Okay, so that's our first concept. The second one that we need to introduce, or I guess talk about in a little more detail, is emission from real surfaces. So we talked about this a little bit last week, just to write down the definition of the total emissivity. But we also talked about how emission from a real surface can be preferential for a given direction or wavelength. So you can define a directional or spectral emissivity, and that can vary depending on the specific wavelength or direction of radiation emission that you're interested in. So for a given surface, the total emissivity is averaged over all of the wavelengths and directions, and so that's only a property of the temperature. It only varies with the temperature for a given surface, which you should have seen if you've looked at the emissivity values in the back of the book. For a given type of material, you typically have total emissivity values listed as a function of temperature. But for spectral or directional emissivity, because the surface can emit preferentially in some directions or at some wavelengths, you have different values of those emissivities depending on which direction or wavelength you're specifically interested in. Okay, so just for comparison, we'll first write down the total emissivity, which we've written down before. And this is a function only of temperature, and it's defined in terms of the total emissive power of a real surface divided by the total emissive power of a black body at the same temperature. So like I said, that's the emissivity averaged over all directions and wavelengths of interest. So the most general emissivity is the spectral directional emissivity. And that is epsilon sub lambda theta. And that's a function of the wavelength, the direction, and the temperature. And it's defined in terms of our spectral intensity. So remember, the spectral intensity is the amount of radiation leaving at a given wavelength in a given direction for the unit surface area, etc. And again, at a given temperature, divided by the spectral intensity of a black body at that same wavelength and temperature. And because, again, black body irradiation is diffuse, the directional dependence is removed from the black body intensity. So basically, it's the spectral intensity is the same in any direction for a black body. And then just like the derivation we went through when we were developing definitions for the spectral intensity and then the spectral emissive power and the total emissive power, we can integrate over the spectral directional emissivity and take the average, take the directional average to give us the spectral hemispherical emissivity. So again, this is a directional average of this quantity. And it's defined in terms of the spectral emissive power. So if you remember from several lectures ago when we were first talking about spectral intensity, the spectral emissive power is just the spectral intensity integrated over all of the directions theta and phi. So here we're just doing that again, and then we have the spectral hemispherical emissivity in terms of the spectral emissive power. So now we're considering just variation with wavelength. Okay, we can write down analogous expressions for the absorptivity. So for a black body, it absorbs all incoming radiation, so the absorptivity is just 1. But for a real surface, the total absorptivity is the fraction of incoming irradiation that is absorbed. And again, we've written this down previously. So this is averaged over all of the wavelengths and all the directions of incoming radiation. But like with emissivity, absorptivity of a surface can be preferential. So a surface can absorb radiation better if it comes from a certain wavelength or a certain direction. So most generally, we can write the spectral directional absorptivity. These definitions will be useful later. So that's the absorptivity as a function of wavelength and direction. It's typically independent of temperature, or varies only slightly with temperature, which is different from the emissivity. So that's the spectral intensity of the absorbed irradiation divided by the spectral intensity of the total irradiation. And then, as before, we will average that over all directions, and we'll get the spectral hemispherical absorptivity. So that is alpha sub lambda, which is now just a function of lambda, is the spectral absorbed irradiation divided by the spectral irradiation. And again, this is this integrated over all the directions. So another interesting thing to note about absorptivity, so it does not depend on temperature, unlike emissive power, but even the total absorptivity of a surface can vary depending on the nature of the irradiation. So for the emissivity, you typically have one surface, you know its properties, and you can kind of tabulate values of the emissivity. But for absorptivity, because how much radiation is absorbed depends on the nature of the incoming irradiation, you can't just write down tabulated values for the absorptivity. So this can vary, even the total absorptivity can vary for a given surface. Okay. Okay, so now we're going to introduce Kirchhoff's law, which uses some of these definitions that we've been writing down. So this is a very useful concept, and what it looks at is basically trying to define under what conditions you can say the emissivity and the absorptivity of a surface are equal. So it's much easier to determine the emissivity of a surface, but the absorptivity, like I said, is a little more difficult to figure out. So if you can say that the emissivity and the absorptivity are equal, that simplifies a lot of problems. So for this, we're going to define under what conditions emissivity equals absorptivity. That's the total emissivity and the total absorptivity. Specifically for real surfaces. These are always equal for a black body because the emissivity is 1 and the absorptivity is also 1. So we're going to bring back our large isothermal enclosure. So we'll develop this condition first under, or develop this relation first under very restrictive conditions, and then we'll kind of back off and show that it can be also true under a few kind of lesser restrictive conditions. So first, consider a large isothermal enclosure. Surrounding several small objects. So we've got an enclosure. We'll have 3 different objects of different surface areas, which are all small compared to the area of the enclosure. The inner surface of the enclosure is isothermal and is at a temperature T sub S. Each of the surfaces emit radiation, so they have an emissive power E1, E2, and E3. And then irradiation coming from the cavity, because it approximates black body behavior, the cavity does. The irradiation is just emission from a black body. So again, there's no reflection because the reflections are all absorbed. Okay, so the objects experience black body irradiation. And then we're going to assume steady state conditions. So we just have an enclosure with objects in it. There's no heat going in or out, and they've just been sitting there and have come to thermal equilibrium. So they have a finite temperature, the objects do, and the enclosure does. So they're still all emitting radiation and receiving radiation, but because they're at thermal equilibrium, there's just no net radiation exchange. So we'll assume steady state. The system is at thermal equilibrium. There's no net energy transfer. So, for that to be true, the temperature of the objects, the temperatures of the objects must all equal each other and the temperature of the enclosure. If there was a temperature difference, net radiation or net heat transfer would be occurring. Okay, so we're going to apply an energy balance to one of these objects, A1. So we'll start with our general form of the first law. The object A1 is closed. It's at steady state. There's no energy generation. And no work occurring at the boundaries. So that just leaves us with the heat transfer in must equal the heat transfer out. We're interested in changes in the thermal energy of the object. So irradiation that is absorbed is what changes the thermal energy of the object. Reflected radiation does not affect the thermal energy. And then the energy out is going to be the emission of radiation. So for the energy in, we have the absorptivity of object 1 times the total irradiation. So this gives us the fraction of the irradiation that's absorbed per surface area. And then if we multiply by the surface area of the object. And then the emission is just the total emissive power at the temperature of the object times the area. We can simplify this down a little bit. So we said the irradiation is going to be due to emission from the black body cavity at T sub S. And then we said, because it's at thermal equilibrium, all of the temperatures must be equal. So we cancel the area and reduce it down to this expression. And then we can divide through and show that the total emissive power of the object divided by its absorptivity is equal to the emissive power of a black body at the same temperature. We can repeat this for every object in the enclosure. And because for every object in the enclosure, this expression is equal to the emissive power of a black body, they're also going to be equal to each other. So repeating that, that's the emissive power of the first object divided by its absorptivity is equal to the emissive power of the second object divided by its absorptivity for all objects within the enclosure is equal to the emissive power of a black body. And then if we divide through by E sub b, we end up with the emissive power of the real surface divided by the black body, and that's just the emissivity. So we get to the expression that the emissivity is equal to the absorptivity. And the specific conditions that we developed this under, which are very important to keep in mind. So it's true if the surface irradiation, so the irradiation experienced by the objects, corresponds to emission from a black body that's at the same temperature as the surfaces. So this is a pretty restrictive condition, and it's entirely dependent on the nature of the irradiation. And we'll go through some derivations that enable us to apply this law in a few kind of less strict conditions. Okay, we can repeat this derivation for the spectral properties. And show that for the same conditions, the spectral emissivity is also equal to the spectral absorptivity. So that's true for this highly restrictive condition, but it's also true for some less restrictive conditions. And we'll develop those a little bit later. So it's definitely true for the setup that we derived, where the surface irradiation corresponds to emission from a black body at the same temperature, and also for other conditions. Okay, we can also write this down for the spectral directional properties. And this is a really useful expression because it's always true. So the conditions under which we derived this first expression depended on the nature of the irradiation. But the spectral directional emission and absorptivity are properties of the surface itself, and they don't depend on the nature of the irradiation. Because you're only interested in the emissivity or absorptivity for a given wavelength and a given direction, you kind of taken the variation of the irradiation out. So for a surface, it'll have just one value of the spectral, directional, emissivity, and absorptivity. So you can say this is always true because these properties don't depend on the surface irradiation or the nature of the irradiation. So this is always true since these are inherent surface properties. Okay, so we're interested in the conditions under which these expressions can be true, less restrictive conditions under which they can be true. And we will develop those through this concept of the gray surface. So we're going to start with the least restrictive equality and then kind of progress to the most restrictive. So we know this is always true. So now we want to say, okay, let's move just to the spectral properties. So under what conditions, aside from the highly restrictive conditions that we developed, does the spectral emissivity equal the spectral absorptivity? Okay, so to show this really clearly, we have to write out kind of the really long integral expressions for these quantities, which I'll do once, and then we'll step through it. So this is kind of going back to our definitions of the spectral intensity, and I didn't show this explicitly, but you can pretty easily go back through the different definitions that we've written out for these expressions and show that the spectral emissivity is this quantity. So that's the integral of the spectral directional emissivity over all directions divided by the integral over all directions. And this comes from basically having the spectral emissivity is the spectral emissive power of a real surface divided by the spectral emissive power of a black body. And so you can express those in terms of the spectral intensity and kind of rearrange some things and show that it equals this. Okay, and then for the absorptivity, similar thing. Okay. So this is in terms of the spectral directional absorptivity times the intensity of the irradiation. And then the intensity of the irradiation in the denominator. And there are two conditions under which these quantities could be equal. Okay, so the first is they're true if the irradiation is diffuse. So that enables us to say the spectral intensity of the irradiation is independent of theta and phi. So we really needed to write these out in order to kind of look at them and understand why this condition allows them to be true. So first of all, we know that the spectral directional emissivity and absorptivity are always equal. So if you go ahead and take those two as equal, then if you say the irradiation is diffuse, this quantity, that means it does not depend on direction, so it's a constant with respect to integration over direction. So you can pull that out in front of the integrand for both the numerator and the denominator. Those cancel. And then, because these quantities are equal, you're left with basically 1 equals 1. So if the irradiation is diffuse, which is a much less restrictive situation than if it's irradiation from a black body. And then the second condition is if the surface is diffuse. So basically its emissivity and absorptivity is independent of direction. So regardless of the nature of the incoming radiation, the surface will absorb the same amount of that radiation from all directions and also emit the same radiation in all directions. So emissivity and absorptivity and that just enables us to bring these quantities in front of the integrand. And then because they're equal, they cancel, and then you just have 1 equals 1 on both sides of the equation for that, that condition. Okay, so we'll stop there, and then Wednesday we'll further talk about the additional conditions under which the total emissivity equals the total absorptivity. And then tomorrow is recitation. We'll do final exam review. Also, your lab is due, and then homework due Wednesday. Okay, thanks.